Hi, I am Shahnawaz. In last lecture, we were discussing epimorphisms. So we said that an epimorphism in a category is same as a monomorphism in the dual category. So if we have a category A and let us consider this dual category, say A of. So if we have a morphism here, say F, which is given to be a monomorphism. So its dual version is called an epimorphism. So we have F of here. So this is called the epimorphism. So let us define it once more. So we have the definition of an epimorphism. So let us consider a morphism, say F from object A to object B. So B a morphism in a category A. So then F is called an epimorphism uh, if for any arrows say G and H from say object B to any object X, if G composite F is same as H composite F, so this should imply that G and H are equal. So this is what we call an epimorphism. An epimorphism is also sometimes called as epic or epi. Now we have a proposition here. So a set function say f uh, in the category set. So here the category set. So a set function is epimorphism if and only if it is surjective. So is an epimorphism if and only if it is surjective. So here is the proof. So first we are going to assume that this f is this f is surjective, and we'll prove f is epi. So suppose f, which is a morphism from object A to B, suppose this is surjective. Now to prove it is epimorphism, so now since f is given to be a surjective, that means if we choose any element inside B, we can always find an element in A whose image under f is B. Now to prove this f is surjective, epimorphism, we have to consider two arrows. So let us consider two arrows, say G and H. So let G and H be arrows from object B to object X. So they are two functions. such that G is not equal to H. So one should note here and the contrapositive definition of an epimorphism is that if G is not equal to H, this should imply G composite F is not equal to H composite F. So here we are going to use this definition to prove this F is an epimorphism. So such that G is not equal to H. So if G and H are not the same, then there is some element inside B at which they do not agree. So then there exists some element, say B in B, such that G of B is not same as H of B. Now, since F is surjective, there exists an element, so we have chosen this B inside B. So since F is surjective, therefore this for this B in B there is some A in A whose image under F is B. Therefore there exists A inside A such that F of A is B. Now B is same as F of A. So this follows from the fact that F is surjective. So this would imply G of B, but B is same as F of A, is not same as H of B, which is F of A, or this would give us G composite F at A is not same as H composite of F at A. Now that means this morphism G composite F and H composite F, and they do not agree at some point, hence they cannot be equal. So hence G composite F is not equal to H composite F. So this means this F is an epimorphism. So now conversely, suppose that now what we are going to assume, we are going to assume that we have to prove now that if F is given to be epimorphism, then it is surjective. But to prove this fact, we use a contrapositive statement. We are going to assume that F is not surjective, and we will end up showing that F is not an epimorphism. So conversely, suppose uh, F is not surjective. Uh, so if this is the case, this would imply that there exists some element A in A. Sorry, I mean there exists some element B in B for which there is no element A in A, such that F of A is B. So then there exists some B inside B for which there is no A inside A, such that F of A is equal to B. Now we are going to define two arrows. So define G and H from object B to the set A, to the set say 0 1, as follows. So we are going to assume that G and H agree at all the points of set B except at B itself, I mean little b. So they agree at all x inside B except this little b. Now at little b we are going to assume that G of B is 0 and H of B is 1. Now one can note here that G and H, they are not the same functions because they do not agree at B. However, if we look at the composite map F, G composite F and H composite F, they are the same. So then uh, G is not equal to H, since G of B is not equal to H of B. But G composite F is same as H composite F. And the reason for this is that B has no preimage in A, since mm, F has, sorry, since B has no preimage in A. So here we have, I mean, since G and H agree at all the points, so we had to only worry for the point B. But knowing the fact that B has no preimage in A, we can easily say that these two maps are equal. So this means that F is not epi. So this shows that F is not an epimorphism. Now we are going to discuss one of the important concepts in category theory, uh, that is the functors. So in category theory, it is morphisms rather than objects that have the primary role. So one of the lessons in this theory is that whenever we meet a type of a mathematical object, I mean any type of mathematical object, we should always ask whether there is a sensible notion of a map between such objects. So we can ask this question about categories themselves. For example, if we have say a category where the objects are categories, so say we have a category, say let us call this cat. So this is the category of categories. So now here the objects are the categories themselves. Now it is natural to ask, is there any map from this object to this object? So and the answer for this question is yes. Such a map between categories is called a functor. Now here is the formal definition. So we have the definition of a functor. So let us consider two categories. So let A and B be categories. So a functor, uh, let us note this by this fancy F, from category A to category B is a function. So this is a function that associates first, so that associates with each object A inside A, an object FA inside B. So that means a functor maps objects to objects, and naturally it has to map morphisms to morphisms. So with each morphism, let us suppose the morphism is F, which is from the object A to A prime in the category A. So this functor F assigns this little f a morphism. Let us note that by f of f. So this morphism uh, is between the objects f of a and f of a prime. So this happens in the category B. So now this functor is subject to the following conditions. I mean, such that first is that it preserves the identity morphisms, such that if we look at the morphism 1 sub a, so it is, I mean, uh, this is the identity morphism on a, and we when we evaluate this functor at this morphism, we get the identity morphism on this object f of a. So that is, this f preserves uh, this f preserves uh, identity morphisms. And the second condition is that f preserves the composition, i.e. f evaluated, I mean f of the composite morphism, say f composite with f prime, is the morphism f of f composite f of f prime. So whenever these two morphisms f and f prime are between the objects, say a, b, and c, so let us call this a prime and a double prime. So here we have the morphism f prime, and here we have the morphism f f. So this is in a. So uh, this means that this fantasy f preserves the composition. So that is, this fancy f preserves the composition. Now we want to fix a notation here. So the functors from category A to category B. So functors from category, say A to B, will be denoted by, will be noted by, so we just notice by this arrow, or with A and B and the arrow F. So also we denote the action of this fancy F on both objects and morphisms by. So also we denote the action of uh, this fancy F on both objects and morphisms by. So if we have a morphism between A and B in the category say A, then when we evaluate functor F over it, we get the morphism between the objects F of A and F of B, and the morphism over here is the morphism F of F. Now let us do some examples. So the example first. So for any category, we can always define the identity functor, which takes the object to itself and a morphism to itself. So for any category, say this fancy A, there is the identity functor. Let us note this by one sub this little a. So this identity functor is from category A to category A. So this is defined by. So if we have a morphism between objects A and B in category A, then the identity functor over it gives us the output. I mean the same output. Similarly, we can define the constant functor. So for any categories, say fancy A and B, and any object, let us fix some object, say this B inside the object class of B, there is a constant functor. So this constant functor we know this by C sub B. So this is the functor from category A to category B, which takes the so so this is the functor from category A to category B, such that if we have a morphism between objects A and A prime, and we have a map F here, then the category the constant functor sends this pair to the pair B to B, and this goes to identity on B. I mean it sends any object to object B, so this B is fixed, and uh, any morphism to the identity morphism on the object B. Now we have one more example here. So for any category A, while the objects are equipped with some structure, there is uh, the functor which we called the forgetful functor or the underlying functor. Now, what this functor does, it forgets the structure of the objects, and it just carries the objects with some structure to just the underlying set. So for any category, say A, where the objects are equipped with some structure, there is the forgetful functor. Or this functor is sometimes called as the underlying functor. Now, this underlying functor takes a category A into the category set. So each where in each case where in each case UA is the underlying set of uh, the object A of category fancy A, and UF, which is same as F, is the underlying function of the morphism, is the underlying function of morphism. F. So, for example, U takes the category group, I mean the category of groups to the category of set. So this U takes the pair, say G to H, or let us know this by G prime. So it takes it to the UG prime, and this is UF, which is same as F. So here G and G prime are groups, and F is a group homomorphism, and UG and UH are satisfied as UF is just a set function. So where G and G prime are groups and F is a group homomorphism. And UG prime are sets, whereas this F, or let us note this by UF is the set function. Now the I mean forgetful functors do not have to forget all the structure. Uh, here this forgetful functor forgets all the structure of the objects in the category group, but it is not necessary. I mean, forgetful functors do not require to forget all the structure of objects. For example, so let's make a remark here. So forgetful functors do not have to forget all the structure, all the structure of the objects. For example, let us consider the category say AB. So let AB be the category of abelian groups. So then the functor, let's say, let us call this U from the category of rings to the category of abelian groups. So this functor forgets the multiplication structure um, of the objects in the category ring. So but it remembers the additive structure of the group, I mean the objects. So this forgets the, because a ring, I mean, the difference between a ring and an abelian group is that the abelian group, when we give it a multiplication structure, we get a ring. So it forgets the multiplicative structure of the objects in the category ring, but but remembers, so but remembering the underlying additive structure. Now we have one more example. So this is about the free functors. Now these free functors between categories, they are in some sense the dual to forgetful functors. So there are free functors between the categories. So these functors are in some sense the dual uh, to forgetful functors. So let us give some example. So for example, we had the free functor. Let us call this uh, say, let us call this E from the category set to category group, or from the category set to the category of vector spaces. So now what this functor does, it gives the structure, I mean the group structure to, or some vector space structure to some sets. So if you are given a set, then we can make a group out of it by using the notion of free groups.